Hello, in this video we're in the multiple linear regression setting, and we're going to develop a way to simultaneously make inferences on this beta vector, or all the beta parameters at one time. We're going to use a multivariate approach, and we're going to use a Bonferroni approach. So here we assume that our regression model is y is equal to x beta plus epsilon. And this is the error term, and this is a k plus 1 by 1 vector. Since we're going to make inferences, conduct confidence intervals, etc., we need a distributional property. We're going to assume that the epsilons are multivariate normal with mean vector 0, variance covariance matrix sigma squared I. So in previous video 32, we showed that beta hat was multivariate normal with mean beta and variance covariance matrix this. Then we also showed in previous video 32 that when we want to make an inference about an individual beta parameter, and we did it this way, where we let EI transpose times beta hat. So this is the k plus 1 by 1 vector, and E is a vector of all zeros except for 1, 1 in the ith position. So when you multiply these together, it cancels out everything but the ith beta. And it was multivariate normal with mean beta I, so it's unbiased, and it had a variance of sigma squared CII, where CII is the ith diagonal element of this, X transpose X inverse. And again, previous video 32 in this playlist. So an unadjusted confidence interval for a particular beta I would be this. So we come up with our beta I hat, so that's the least squares estimate, plus a t random variable, plus the standard error associated with this beta I estimate, beta I hat estimate. And this, you can actually go to PV32 for a little more detail on that. But notice here that this right here is what we were calling CII. So this is X transpose X inverse, right? And if we pre and post multiply it by that EI vector, it actually grabs that II diagonal element from this. So this is what we were calling CII. Now, a Bonferroni adjustment, and previous video 16 in this playlist has maybe a little more if you want to review that video. So the experiment-wise error rate is the probability of making at least one type 1 error over all the comparisons of interest. And so the more you look for things, the more you find, the more chance you have an error also. So the more you look without adjusting the alpha level at each individual comparison, your probability of making at least one type where error goes up. So we want to somehow control this experiment-wise error rate. Now some people call it the family-wise error rate, but here we're going to call it the experiment-wise error rate. So we want to construct R confidence intervals. So that's our goal. There's R beta parameters that are of interest to us, and that's what we want to look at. So to maintain the experiment-wise error rate at the alpha level, we conduct each confidence interval at the 1 minus alpha over R % level. So we want R confidence intervals, we divide by R. Now here's a quick little proof of this. So let CI be the confidence interval for beta I, and this is for all, for the first R betas, and that's less than K. It could equal K, but we're just going to call it R generically. So let's let AI be the event that CI captures beta I. So now the experiment-wise error rate, remember that's the probability that we make at least one type 1 error. So that's the probability that we don't capture the true beta, for beta 0. So that's the complement. So we make a type 1 error on beta 0, or we make a type 1 error on beta 1, or we make a type 1 error on our last comparison. So if we make a type 1 error on any of these, the probability of that happening is what we call the experiment-wise error rate. Now, by Boole's inequality, this union of events is actually less than or equal to the probability of the sum, right? But each individual, we know this, the probability that we make a type 1 error on on beta 0 is actually alpha over R, right? Remember, we're conducting each test at the alpha over R alpha level. And there's R of these, so each one of them has the same probability of alpha over R. But when these are added up, that's alpha. So the experiment-wise error rate, if we use this Bonferroni approach, protects the experiment-wise error rate at a maximum of alpha. Okay, so that means if we want to do simultaneous confidence interval for all the beta parameters, beta I, so that's 0 through k, right? So this is a k plus 1. Oh, that's just a scalar. But all the betas, there's k plus 1 of them. So that means we conduct these k plus 1 confidence intervals on each beta at the alpha over k plus 1 level. Now remember, to construct confidence intervals, you take alpha over 2, but the overall alpha has to be divided by k plus 1. So we conduct all these confidence intervals at this level. And this right here is the standard error associated with that beta I parameter. And that's it. So that's the Bonferroni approach to simultaneous confidence intervals on all the beta parameters. Now let's do a little multivariate approach for confidence intervals. We have shown that beta hat is multivariate normal. So if we subtract its mean, which was beta, it becomes multivariate normal with mean 0, but it has the same variance covariance matrix. Now we're going to defer to my videos called Distribution of Quadratic Forms, where we can just instantly know distributions. So here we take this vector, of course transpose, and then we take the inverse of this. So that's why this goes down in the denominator. And the inverse of an inverse is just what we started with. And of course that vector. And then watching these videos, you can instantly know that that's a chi-squared with k plus 1 degrees of freedom. K plus 1 is the rank of this matrix here. And since X transpose X is a k by k matrix and it's invertible, we know it has k plus 1 degrees of freedom. So now we use this and create an F distribution, mainly because we don't know that. If we knew sigma squared, then we can isolate the beta and create some sort of interval to estimate beta. But we don't know sigma squared, so we have to do something different. Now this piece here is a chi-squared, and let's divide by its degrees of freedom. And this is the sum squares of residual divided by sigma squared is a chi-squared. Let's divide by its degrees of freedom. Then this becomes an F distribution with k plus 1 and n minus k plus 1 degrees of freedom. Now the random components, beta hat and sum squares of residual, are independent, and we've proved that lots and lots of times on previous videos. So those two are independent. Well, now to create a 1 minus alpha % confidence interval, confidence region for the beta parameter is this. We create this right here. If we let this interval, which is actually this right here, right? Beta X transpose X, this comes out. The sigma squareds cancel. Sum of squares residual divided by this is what we were calling the mean square error, or our unbiased estimate of our error variance. Of course, the k plus 1 comes down. If we let this be less than an F alpha cutoff level, then the probability of being less than that is 1 minus alpha. So all the betas that satisfy this, it creates a confidence region for beta, right? Now, in R, to plot this region is sort of tough because they don't have built-in explicit plot functions. But if you use like Maxima or MATLAB or Maple, or there's math programs that explicit plot, and then you can actually find a region for this beta parameter. Well, that's all I have for this video on simultaneous inference on the beta vector. I hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.